Thank you. So, some brief genealogy how this talk came about. Currently, I'm working as head of analytics at GoOpti. GoOpti is a Slovenian startup who does on-demand shared transports, long-distance transports, mostly to and from airports. You can think of it sort of like Uber Pop, only we manage to usually pack our vans with 5+ people. So for us, data science is not just something that's nice to do alongside with marketing and so forth, but it's the core of what we do. Before that, I spent a couple of years doing consulting work and helping companies become data-driven. So all the remarks from today are based on both being an outsider and helping companies become data-driven and also being in charge of doing the same thing and seeing where are the biggest friction points. So, and a small comment before I really delve into it. What I'm going to talk about is not overly applicable if your data is really big, but on the same time, I think that not a lot of us actually have big data as such. I think that if you're a bit smart with how you do your ETL, you can handle most of the data loads on a single machine. So have this in mind. If your data is really amazingly huge, then these things are going to suck for you and you need to look for other things. But as I said, I think most of it can be done on a laptop, and I also think it's quite important that we manage to convert our data in such a form that it can be done. So why? Because, and here I'd like to talk about the, shall we say, lessons learned in a very abstract way about doing data science. I think the biggest takeout for me, and this is the one thing I want you guys to take from this talk, if nothing else, is that there are this kind of different timings in terms of how long it takes for a data scientist to provide an answer. And ideally, you're looking at providing answers in 2 minutes and less. This means that when you're in a brainstorming, you can just pull out the data and influence the conversation. And this is how data should be used. When talking about being data-driven, this is the ideal we're striving for. Now, obviously, not everything can be done as such. So I think that the next class of how hard the problem is to solve is about less than 20 minutes. This still means that you can sort of probably stuff it somewhere in your day and be done with it. And then you have this chasm where it takes so long that it's becomes disconnected with the needs of those who are asking for you, and it's still probably not very important. So it's not a project which you would put on a roadmap and so forth, but just sort of lounging around in your inbox or a ticket and you're waiting some time to be done. So my focus is into trying to basically obviously focus on the first part of this timeline. So trying to solve most problems in 2 minutes and failing that in 20 minutes. And again, this is also why I think it's important that even if you have super big data, you try to transform it in such a way that you can work with it fast, because the bigger the data, the longer it just takes to the whole thing to compute, and then if just computing takes an hour, you obviously can't have an answer in 2 minutes. The second thing is, and this is quite well established in data science, but I think also that it bears repeating, is try to think in terms of distributions, therefore visualize everything at every possible opportunity. There is an amazing richness of data that you're losing if you focus too fast and think just about various averages and so forth. So always try to think with distributions in mind. So therefore, we need an environment which allows us easy visualizations. The third thing is no throwaways. You do this one-off analysis and think, oh, I'll never need it again, and it gets lost somewhere. Don't do that. Always try to have an audit trail in terms of commits into a repository. And also this gives you an ability to come back to the analysis you already did. And this becomes relevant incredibly often. Either because somebody needs the same thing you did, even though you thought, I'm going to never need it again, somebody will need it in half a year's time. And also, maybe it turns out that there is some inconsistency somewhere, and you try to track down where the misinformation came about. And then it's very useful that you can find all the steps that you did to provide an answer, not just that some other person in your team has an Excel with the answer, which now becomes problematic. And the last thing is, think about how you share the results. It's not just that you come up with a result, but this is just where the life cycle, in a way, starts. Now, it's the question is, what can we do that? How can we share it with other people who are also invested in data and who actually need the answers? I think the first important thing is to always have just one canonical version. This means no sending files of any kind over email, because then there are 5 versions and nobody knows which is the latest one, and probably none is. So we want something that allows us to have live data in one place, and we all agree this is the version that we accept as the ground truth. The second thing is, it also would be great to be able to concentrate all the conversations around this analysis in a single point. Because what the usual workflow for a lot of people is that you send some result over email or on a Slack channel or whatever, and then people talk about it, and then it gets lost. And it's a problem when you get new people on a project or you're revisiting something old, and it's very hard to find all the relevant discussions because they're spread around. So again, the same as you have a canonical version of your data, also try to concentrate all the discussions around it. And the last thing is include methodology, meaning code. Don't just produce a graph, stick it into Excel or something, and fire it off, but have code along with it as well. Because at some point, a question is going to arise as to how exactly did you calculate that, and then if it's in the same place, the answer is much faster than looking through the various repositories and so forth. So with these 4 principles in mind, what is my current working environment like? Now, here is the first point of contention or debate. Should the development be notebook-based or REPL-based? Both have their pros and cons. The obvious pro of REPL is that most of the Clojure tooling and ecosystem sort of anticipates it, so you get much better tooling out of the box. But at the same time, I think that the notebook is a much more natural environment for doing exploratory data science, because the problem with a REPL is that it's too ephemeral. It's sort of you explore, but also the previous results get lost. And they're ordered strictly chronologically, while I think that a lot of times when working with data, you want to sort of revisit some parts, and it's very convenient to continue on in some cell upwards. But of course, the best solution would be, why not both? And I think that this is something that we should be striving for. Right now, I don't know of any environment that allows that, but it's very simple to imagine sort of clubbering it together from different sources. Now, obviously, the next step would be to have this way more integrated, but I think it, because like, I'm a bad programmer in a lot of ways, and I'm shit with remembering what exactly various functions do, and corner cases with destructuring and so forth. So I always have a lot of completely throwaway code, and it's very convenient to pollute your notebook with such stuff. And on the other hand, for the actual analysis, I definitely want a notebook. So I'm looking for a combination of both a notebook and a REPL. In terms of notebook, the stack that we are currently using is a combination of quite modified Gorilla REPL, and I'm a bad person, so I haven't contributed our changes yet, because they're actually hacks and not really production-worthy, but they sort of work for us. And on top of that, we add an auto-refresh functionality. So each night, all the notebooks get recalculated, so you know that any data that you look on our servers is at most 1 day old. And the last thing we use is hypothesis for just making inline annotations. So the whole thing put together looks like this. This is your notebook, or Gorilla notebook, and then alongside it you get the hypothesis window, which allows us inline comments and so forth. So this basically covers most of the things I want in such a system. It's obviously shareable because it lives on our internal server. Hypothesis allows us to have comments, questions, and so forth inside, and also provides a certain amount of discoverability by just tagging and then having a service which builds an index out of all of these notebooks. And it's periodically run, so it's sort of fresh. And last but not least, by default, all the code is hidden, so people don't get too intimidated by lots of code when they aren't interested in it, but you still can then just say, OK, show me the code, and it sort of works as a normal notebook viewer. And this is workable, but there is a lot to be desired. First of all, I would definitely love a better editor. Otherwise, I live in Emacs, so no, the interface of Gorilla REPL is sort of limiting and depressing. There are some interesting projects now with doing structured editing on the web, so I'm hoping that sometimes down the line something like that can be integrated. As I said, I definitely want an embedded REPL inside the notebook. Right now it's a hack to just have Emacs open and then connected to the same nREPL server. Definitely, and this is a recurring theme, I think, with most Clojure projects, I want better exception reporting, but again, the situation has improved vastly over the last year in the Clojure ecosystem, so I think that if some libraries are integrated, we can have a much better experience here. And last but not least, some way to actually structurally browse data structures. Also here, as a comment, I've tried using org Babel and sort of failed miserably, never managed to really make the workflow as smooth as possible, but it's very possible that this, namely org Babel, is the ultimate solution, just I'm not enough of an Emacs hacker to make it work. So if it's something, if you can make it work, more power to you. I think that this would be the ultimate solution, but sadly, the investment and also just the learning curve doesn't really add up in compared to something like I've outlined here. Now, for the second part of my talk, let's talk about the tools or the libraries or whatever that are being run within this notebook. And here, let's again start conceptually. I think that there is a big problem in how most tools or libraries geared toward data science are produced. And this tweet by GigaSquid excellently encompasses what's the core problem. There's this imaginary divide between doing data science or statistical analytics, whatever you want to call it, on one hand, and doing programming and engineering on the other. And it sort of seems that you have to decide on one and then be burdened with the other one being not very convenient to do. But I think that's, and here completely agreeing with her, that this is a false dichotomy, that we can actually have both if we think about it for a moment. So I have a problem with most data frame implementations that are currently available. Because they sort of neglect that in the real world, data tends to be heterogeneous. And it also, in just concretely in terms of Clojure, Clojure excels at structure manipulation and sort of transforming or re-encoding your problem into a version that's easier to manipulate or easier to solve. But the hidden assumptions with data frames sort of counteract against this. So I think it's a very radically column-oriented data structure is not really the best match for what we're looking for in a Clojure ecosystem. And I also think that the moment you go completely into a column-oriented solution, you also have a lot of friction with the rest of the Clojure ecosystem and so forth. So I wanted something simpler. And this is something that we've been using for a while, and I have hastily released it today. So it has no documentation and it has no tests. It's just code. So you probably have the most context with this talk, but it's still not something I'm proud of. But I really wanted to put something out that you guys can then pursue later. And obviously, I will add the documentation and all that stuff. But this is started as a very loose collection of functions where I was looking at the patterns in my code that were recurring again and again and thinking about, okay, how can I simplify this? How can I have just less to type? Because again, if you are very conscious of how long it takes you to arrive at a certain answer, you at some point have this problem of, I don't want to type too much because typing becomes the bottleneck. Now, one extreme is that you can go the way like Paul Graham went with Arc and just have those obscure two-letter names. And the other solution is to have a rather smart combination of libraries, rather tools that you can connect together and make it work. So, and I opted for the later option. The whole thing is basically just functions, no data frame whatsoever, or in a concrete way, just sort of implied by the operations on it. I was very conscious to make most functions as composable as possible. So, and even where I'm using something of a DSL, it doesn't use any macros, because if you use pure Clojure code or a clojureD structure in your DSL, it makes it way more composable and manipulatable as if you were using macros. It is, performance was not my main concern, but just thanks to transducers, it's reasonably fast, just by virtue that most other things don't really use all the other cores in our machines, and this thing is pretty efficient at that. Again, because it's focused on exploratory programming or rapid prototyping, a lot of times it tries to follow this do what I mean principle. With that, I mean that it sort of tries to anticipate what I'm actually trying to do, and already sorts at appropriate moments, is very lenient in terms of what kind of inputs it accepts and so forth. So to really spend as least time as possible just doing various glue-like operations. Requires minimal buy-in. Basically, you can use any single function and not within your other workflow and aren't burdened with any assumptions or anything like that. And every function supports reaching into nested structures. This is the biggest concession to having something like a data frame. Basically, I assume that most of my data frames are going to be sort of Clojure vectors of maps, but they can also sort of, but it works well enough also just on vectors of numbers or whatever, but the sort of most of the API is done thinking of operating on a vector of maps. And so in terms to assure composability, all the functions are designed so that work very well with pipe operators and partially and so forth. I try to provide curried versions where possible. I know this is a bit contentious in the Clojure world, but I think that currying, automatic currying is a very nice feature, especially because Clojure is so practical in terms of just composing functions, and not just compose, but you have the every pred and some fn and so forth. So we have a lot of functions work on high order combinators, and here automatic currying would be a blessing. So I try to curry when possible. And as I said, all the DSLs are Clojure structures, and they're therefore composable. Here you can see an example where we're basically generating a map of calls to mean based on just taking a range of hours in this case and just calculating means for each hour. And this is done completely computationally, so this is the code that's generated on the fly. And I want to spend some more time talking about composability, because I think that being able to seamlessly compose your functions is one of the keys to quick iterating. Because it lowers the mental overhead if you have a sort of a consistent API and knowing that just I can plug things together and they tend to work. And also you have all the known primitives, so it's faster to read. There's here again, I think there's some friction between what's the best approach for exploratory data analysis and what would be idiomatic Clojure or Lisp code. In the later case, we know that we should sort of, there's this zen of defining small functions and building up from that. But when you're just trying to extract some data or see something of how a distribution looks like, you don't really want to first write 5 functions and then use them, but you sort of just want to do the whole thing in line. And in that case, composability becomes way more important. And as I said, also just having functions that can be built from other functions. Here again, just I'm a big user of compose and the other combinators, let's say like every pred and so forth. And this again gives you a lot of the power that we're otherwise using macros for, but without all the downsides of macros. So it's a very good solution, especially in such ad hoc cases where you don't actually want to really think through all the combinations which define your own language, your own DSL with Intel. And of course, knowing that I want my functions to work well with pipe operators and partially and so forth already gives me a consistency in terms of the API, which again is important when you're trying to iterate quickly. Now on that point, something that's also important is catching errors early, because the closer to the point where there's actual error, the whole thing explodes, the more context you have, it's easier to debug, and therefore you can also iterate faster. So a bit paradoxically, I think that in exploratory coding, having some sort of a type system is actually a very good thing, even though it's usually type systems are considering something that slows you down in a way. But here I think it can help immensely. What I'm using here in Huri is prismatic schema. I think that there are also other wonderful options available. I picked this one for no really deep reasons, except that it sort of meshed well with my thinking. But the main point is that I think that this is a good case of where some limited type checking is very helpful. Otherwise, a very common problem when working with Clojure's maps is that you sort of mistype or something, a key, and then you get nils, and the whole thing is going to explode some point very, very far down the line, because nils are a valid input to so many functions. Like most sequence functions will take a nil, and then the whole thing just gets completely away from the source of your error, and just takes longer to debug. And even if it takes 2 minutes instead of 30 seconds, this is an overhead I'm not really willing to pay. But of course, we can do better. Here, I hope most of you have seen the wonderful talks by Brad Victor, where he's showing various interactive development environments and interactive exploratory environments. And I'm hoping that some of the ideas are also going to trickle down into tools we're using. And like the first thing I would like, and this is very simple, it's actually, I made a rough prototype here, is to just know for each step when you're using a pipe operator, for each step, just seeing what the output was, because this allows you again to understand better what's happening and find out errors quicker. Of course, this is a very rough prototype, but if every of those outputs would then be explorable, sort of browsable and so forth, we suddenly have quite a powerful system which shows us what's happening as we go along. And this is something that I don't think it's particularly hard to do if you limit the scope enough, and would be of real help. So there are still some missing parts of our tool chain. First of all, machine learning. Now everybody who does data science uses at least some machine learning tools, and both Clojure and Java ecosystems are not really the best for that. So my solution is just farm it out to scikit-learn or whatever you want to use, R, whatever. Most of those libraries, because with machine learning, just using the core library, if it's well-defined, it's very trivial, so it's no problem to just generate a program on the fly or piping it through command line or whatever. And I think it's a good solution, again, for exploratory analysis, but when in production, it probably won't cut it. Like, for instance, if you just want a recommendation, we're using mostly neural networks, and deep learning 4J is an amazing library. So if you're in Java world, if you're in Java world, this is highly recommended. I took the same approach with plotting, where I built a DSL on top of ggplot. Again, this is sort of tightly integrated with the Gorilla REPL I'm using for a notebook. Otherwise, it follows most of the design philosophy I was outlining before, and provides currently all the chart types I'm commonly using, and outputs relatively decent charts. Here, relatively decent compared to something like Incanter, which produces really ugly charts, and the ggplot is very smart in terms of layout and so forth, so you get a lot of bang for your buck. Again, here I'm a big proponent of sort of don't make me think too much, rather do what I mean, and having the library figure out most of the small details and just make it look pretty and functional and so forth. Here again, I have a huge wish list. I would like even better structure manipulation. So when reaching into structure and working on something deep inside, right now I'm using key functions like in the Clojure core standard library, but I think that there are better solutions. For instance, the Spectre library looks very promising. I would like the plots that you've seen, they're right now static SVGs. Being interactive would be nice. Having more transducer compatible and therefore faster mathematical operations, again, would be nice, and it's something that shouldn't be too hard to write. And last but not least, having optimizing piping commands which sort of rewrite the various combinations of those functions to a more efficient version where possible, using more transducer composition. This is something that I'm sorely missing in the Clojure ecosystem, and a great thing that Common Lisp has, and this is compiler macros, and doing something like that on a limited scope would bring us some of the power in terms of optimization of that. Now, to end it off, some projects, and I know this is probably quite useless when I'm talking, but for those of you then who will be looking at the slides, all these projects have either influenced me in some way or are mostly stuff that I want to explore, potentially use, or are similar approaches to the things I've been exploring here and are definitely worth having a look at. Including the first Krastens thing library, which is amazing and makes me want to have a second look at Viga. So with all this, I turn to you, and if you have any questions.